Hello everyone, my today's topic is survivability with AIDS. AIDS, or generally known as HIV. So HIV is directly infected to CD4 plus T cells. And these are present in human body. Now the basic number of reproduction of these cells or the HIV cells is represented in R0. R0 stands for the reproduction of these cells. Now, it is determined by R0, either it should be less than 1 or R0 should be greater than 1. Now, if R0 is less than 1, the disease-free equilibrium is asymptomatically stable and the disease dies out. Now, if it is greater than 1, a unique endemic equilibrium exists and is globally stable in the interior of a feasible region. Now, in the DDE model, the delay stands for the incubation time. We prove the effect of that delay on the stability of the equilibria. Now, let us see what does this HIV stand for in, or a simple dynamic model in ODE for HIV is dV by dt is equal to P minus CV. Now, where P stands for an unknown function. C is a constant that is called as a clearance rate constant. And V stands for virus concentration. Now the population dynamics of CD4 plus T cells in humans is not well understood. And HIV stands for human immunodeficiency virus. So now, a reasonable model for this population of cells is, that is for T cells, is T is equal to S minus dt plus AT of 1 minus T divided by T max. S represents rate at which new T cells are created. D is the death rate. And this will happen per T cell. Tmax is the T cell population density. Now this will occur at the proliferation part. And when Tmax occurs, the proliferation will shut down. Now proliferation stands for the reproduction of T cells. T cells can reproduce automatically. A cell, we have already studied about cell division, mitosis and meiosis division, whereas when it comes to cancer, the HIV part, T cells will reproduce by themselves. That part is called as proliferation. Over here what happens is, I can take a T cell . So now this T cell, a HIV will get infected over here, HIV virus, and this will either replicate at that time and it will have a very fast growth and it will burst out the T cells, or else it might grow slowly in 4 stages, which we'll be studying further. And this Tmax cell, once when it occurs in the proliferation part, that time this growth will shut down. Like most viruses, HIV is a very simple creature. Viruses do not have the ability to reproduce independently, which I have said it already over here, that it will embed in the T cell, or we are the host for this virus. Now this will insert into the DNA. The RNA present in HIV will insert into the DNA of a human body or a host. After the DNA of the viruses has been duplicated by the host cell, it is reassembled and new virus particles bud form on the surface of the host cell. This budding can take place rapidly or very slowly, which I have already said you over here. If rapidly in the sense, then it will start bursting and killing the host cell. The course of infection with HIV is not clear-cut. Clinicians are still arguing about what causes the eventual collapse of this immune system, resulting in death. So what is widely agreed upon is, however, is that there are 4 main stages of disease progression. Now first stage is initial molecule. Initial inoculum or molecule it is called as. So initial inoculum. Now this first stage where the virus is entered into the body or introduced in the body. Now second stage is the initial transient. Now over here, a relative short period of time when both T cell population and virus population is in great flux. So T cell and virus population are in great flux. What does this mean? This means that these are going on reproducing, or the cell division is taking place over here. The third stage is clinical latency. Now this is a period of time when there are extremely large numbers of virus and T cells undergoing incredible dynamics. Extremely large number of T cells. The overall result of which is an appearance of latency. Now in this stage what happens is the T cells and the viruses will grow rapidly in the second stage. Now over here what happens, we start feeling the disorders. Now coming to the last stage, that is, there is AIDS. Now this is characterized by T cells dropping to very low numbers, or the T cells will become 0, and the virus growing without bond, resulting in death. So when it stops the cell division in T cells and the virus is growing very extremely, then at that time AIDS occurs and that leads to death. So now let us see the ODE model for AIDS. or HIV. So now in this section, an epidemic model of HIV infection of CD4 plus T cells with cure rate and delay is studied. So now we have already studied an equation of T cells. That is T is equal to S minus dt plus AT into 1 minus T by T max. So now if I write dt by dt, I'll get S minus dt plus AT into 1 minus T divided by T max minus beta TV plus rho into I. Now there is another equation, di by dt is equal to beta TV minus rho delta plus rho into I. Third equation is dv by dt is equal to q I minus cv. Now these are the three equations, and I'll consider this equation as equation 2 and I'll take this as equation 1. So now T stands for the number of target cells or the T cells. I stands for the number of infected cells. We know the viral load of virins or the virus that has been spread. dV by dt stands for the rate of virus that has been spread. BTV is a mass action term in which the rate of infection is given by BTV, that beta is beta into TV, with beta being the infection rate constant. T as well as V stands for the same definitions. Thus, in what follows, the classical models assume that infected T cells are at rate beta and the generation of infected T cells are at rate of beta into TV. In this model, S represents the rate at which new T cells are created from sources. A is the maximum proliferation rate. Rate of targeted cells. Tmax is the T population density at which proliferation sets off. D is death rate. Of T cells. Delta is the death rate of infected cells. Infective cells. Q is the reproductive rate of infective cells. C, we already know that C is a clearance constant, and rho is the rate of cure. Rate of cure, that is non-cytolic loss of infected cells. Thus, the total rate of disappearance of infected cells is rho plus delta. The average lifespan of a productively infected cells is 1 by rho or 1 by delta. An infected cell produces a total of Q by delta virions. Q by delta virions during its lifetime. Now variance stands for the virus. The average rate of the virus released by each cell is called Q. Standard and simple arguments are shown in the solutions of the second equation. So now let us see the initial conditions for the second equation, that is t of 0 greater than 0, I of 0 greater than 0, p of 0 greater than 0. Now this we are seeing for the second equation. So now we can denote this as r plus 3 is equal to t I and v belongs to r cube, t greater than or equal to 0, I greater than or equal to 0, v greater than or equal to 0. Now this I'll take it as 2.1 and this as 2.2. So now here R stands for the reproductive rate of the virus. So now let us see the equilibria and the stability. Now I will represent equilibria as E. The non-negative equilibria of the second equation will be T0, 0 as well as 0, and E bar is equal to T bar, I bar as well as V bar. I'll take this as 2.3, where T naught is equal to T max divided by 2A into A minus D plus square root of A minus D the whole square plus 4A is divided by T max T bar is equal to C into delta plus rho divided by beta into Q. I bar is 1 by delta into S minus D T bar plus A T bar into 1 minus T bar divided by T max. And V bar is equal to Q divided by C into I bar. Now I'll take the reproductive rate, the initial reproductive rate, as T naught divided by T bar. It is well known the importance of the value R naught, which is called the basic reproductive ratio of the system of virus. It represents the average number of secondary infection caused by a single infected cell in an entirely susceptible cell population throughout its infection period, and it determines the dynamical properties of the second equation over a long period of time. Based on the result of a differential equation of HIV infection of a differential of CD4 plus T cells with cure rate authorized by Zhou et al. So now we obtain the following results or the theorems. If R naught is less than 1, E naught is equal to T0, 0 and 0 is locally stable, and if R naught is greater than 1, is unstable. Second theorem is there is an m greater than 0 such that for any positive solution t of t, I of t, v of t of second equation t of t is less than or equal to m, I of t is less than or equal to m, and v of t is less than or equal to m for all large t. The last theorem is, suppose that r naught greater than 1 and c plus delta plus rho plus d minus a plus 2a t bar divided by t max into minus d plus a minus 2a into t bar divided by t max into c plus rho plus delta plus beta into v bar into c plus delta is less than 0, then the second equation is an orbitally stable periodic orbit. So now let us see the delay model. In this, we will introduce a time delay into the second equation as well as the 2.1 equation. To represent the incubation time that the vectors need to become infectious, the model for the CD4 plus T cell is exactly as before. dt by dt is equal to s minus dt plus at into 1 minus t divided by t max minus beta into t of t minus tau into v of t minus tau plus rho into I. di by dt is equal to beta into t minus tau into v into t minus tau minus of delta plus rho into I. dv by dt is equal to q into I minus cv. Now I will take the whole system as equation 3. The time delay is introduced in the system describing the dynamics of the healthy cells. At the time t, only healthy cells that have infected by the virus tau times units ago, that is t minus tau, become infectious provided that they have survived the incubation period of tau units and given that they were alive at this time t minus tau when they infect the healthy cells. Thus the incidence term of healthy cells is changed from beta into tv to beta t into t minus tau into v into t minus tau. However, the third equation also satisfies the initial conditions, that is t of theta is equal to t naught, I of theta is equal to I naught, v of theta is equal to v naught, where theta belongs to or ranges from minus tau to 0. All the parameters are same as in equation 2 except for all the positive constant tau, which represents the length of delay. We find again an uninfected steady state is equal to t naught 0 0, and an infected steady state, that is E bar is equal to T bar, I bar and V bar, where T bar, I bar and V bar are same as in section 2.3, the equation 2.3. Since the uninfected steady state E naught is unstable when tau is equal to 0, and R naught is less than 1, incorporation of a delay will not change the instability. Thus E naught is unstable if R naught is greater than 1, which is also feasibility condition for the infected steady state, that is E bar. We introduce the reproduction number of differential delay model of the third equation, which is given by a similar expression. R naught is equal to T naught divided by T bar, which is equal to beta into Q T naught divided by C into delta plus rho. Its biological meaning is as follows. If one virus is introduced in a population of uninfected cells which infect the total number of secondary infections during their infectious period, 1 by C into delta plus rho. Now let us see the local and global stability of the disease in free equilibrium. Now we will study E naught of the differential delay model, that is the third equation. We consider the local stability in two cases. When R naught is less than 1 and R naught is greater than 1. Now there is a theorem for this. I'll name it as the fourth theorem. The disease-free equilibrium E naught of the third equation is locally asymptotically stable if R naught is less than 1. The disease equilibrium is unstable if R naught is greater than 1. Now let us see the proof for this. So now I will linearize my third equation. In third equation, we have already seen the third equation in delay model. So when I linearize this one around E naught is equal to 0, E naught is equal to T naught 0 and 0, we obtain one negative characteristic solution, that is lambda 1 is equal to A minus D minus 2A into T naught divided by T max. And the following transcendental characteristic equation for the disease-free equilibrium E naught, whose solution, real as well as complex, give the remaining eigenvalues. That is lambda square plus delta plus rho plus C into lambda plus C into delta plus rho minus Q beta into T naught e power minus lambda into tau is equal to 0. I will consider this equation as 3.1. For tau is equal to 0, we obtain the same quadratic equation as in ODE. In that case, we know from before that all eigenvalues of this equation, the 3.1 equation, is locally asymptotically stable if R naught less than 1, stable if R naught is less than 1, and unstable if R naught is greater than 1. We expect that in this case 3.1 has a positive root and the disease-free equilibrium is unstable. Indeed, to see this, we arrange the 3.1 equation in this form. T naught e power minus lambda tau minus c into delta plus rho. I'll call this as 3.2. Suppose that lambda is real. I'll denote the left hand side of the second equation as f of lambda and the right hand side as g of lambda. Now we have f of 0 is equal to 0 and limit lambda tends to infinity, f of lambda is equal to infinity. In contrast, the function g of lambda is a decreasing function of lambda and g of 0 is equal to c into delta plus rho into r naught minus 1, and this is greater than 0. Thus the two functions must intersect for some lambda greater than 0. Consequently, 3.1 equation has a positive real solution and the disease-free equilibrium is unstable. Now we turn to the case R naught less than 1. First we notice that the 3.2 equation does not have non-negative real roots. Since in this case f of lambda is increasing for lambda greater than or equal to 0, while g of lambda is still decreasing function of lambda, but g of 0 is equal to c into delta plus rho into r naught minus 1. Less than 0. Thus, if 3.1 equation has roots with non-negative real parts, they must be complex and should have been obtained from a pair of complex conjugate roots which cross imaginary axis. Consequently, equation 3.1 must have a pair of purely imaginary solutions for some tau greater than 0. Now I'll assume lambda is equal to I into omega, and without loss of generality, let me assume omega is greater than 0 is a root of the 3.1 equation. That is the case if and only if omega satisfies omega square plus I into delta plus rho plus c into omega plus c into delta plus rho minus q beta t naught cos omega tau plus I q beta into t naught into sin omega tau is equal to 0. I'll consider as 3.3. Now separating the real and imaginary parts, we have the following system satisfied by omega minus omega square plus c into delta plus rho is equal to q beta t naught into cos omega t omega tau, and delta plus rho plus c into omega is equal to minus q beta t naught into sin omega tau. I'll consider these two equations as 3.4. To eliminate the trigonometric functions, we square both sides of each equation above and we add the squared equations of 3.4 to obtain the following fourth order equation in omega. Omega 4 plus tau plus rho plus c the whole square plus 2c into delta plus rho into omega square plus c square delta plus rho square the whole square minus q square beta square into t naught square is equal to 0. I'll consider it as 3.5. To reduce this fourth order equation into quadratic equation, we'll assume z is equal to omega square. And now I'll denote the coefficients as A10 is equal to delta plus rho plus c the whole square plus 2c into rho plus, delta plus rho, and A20 is equal to c square into delta plus rho the whole square minus q square beta square t naught square. I'll consider this as 3.6. Now we can rewrite the 3.5 equation as z square plus A10z plus A20 is equal to 0. 3.7. Looking back at the coefficients of this quadratic equation, we see that we can expand the square in A10 while applying the formula for the difference of squares to A20. We obtain A10 is equal to delta plus rho plus c square, c the whole square plus 2c into delta plus rho, it's greater than 0, and A20 is equal to c square delta plus rho the whole square minus beta square into t naught square. I can write this as delta plus rho into c into delta plus rho plus beta into t naught into 1 minus r naught. I'll consider these two equations as 3.9. Now since r naught is less than 1, thus the roots of 3.7 have positive product, which means that they are complex or they are real but they have the same sign. In addition, they have negative sum, which implies that they are either real and negative or complex conjugate with negative real parts. Consequently, 3.7 does not have positive real roots, which lead to the conclusion that there is no omega such that I omega is a solution of equation 3.1. Therefore, it follows from Roux's theorem that the real parts of all eigenvalues of characteristic equation 3.2 are negative for all values of the delay tau greater than or equal to 0. This implies that E naught is locally asymptomatically stable if R naught is less than 1. This proves the theorem. Now let us see the simulation of this part. Simulation of the model in this situation shows stable dynamics as presented in this figure. Now this shows the infected as well as the uninfected cells from A to C. They showed that the equilibrium E bar is asymptomatically stable. And virus converge to their equilibrium and parametrical values as stated in the text. They have taken tau is equal to 0.5 whereas S is equal to 5. This shows that the equilibrium is asymptomatically stable. Now using the same set of parameter value as those, as S is equal to 5, I'll vary the tau value as tau is equal to 10 to get oscillations of uninfected and infected cells and viruses. Now I'll consider all these figures as the second figure, in which A to C represents the oscillations of uninfected cells, infected cells as well as the virus. Whereas figure 2D shows that there is a periodic solution or bifurcation. We also find that the infection would always keep stability when the curve rate rho is larger. This can be analyzed from the expansion of R0 and conditions of the theorem, the fourth theorem. For example, the oscillations of uninfected cells, infected cells and viruses from A to C, the diagrams, if we select rho is equal to 0.3, so A is equal to 5 and rho is equal to 0.3, the value of A will be same as it is, whereas the other parameter values will change, and the infection would be differential stabilities. Thus we claim that the curve rate rho is very important parameter. An epidemic model of HIV infection of CD4 plus T cells with cure rate and delay is studied. Mathematical analysis of the model equations with regard to invariance of non-negativity boundaries of solutions, nature of equilibria as well as permanence and global stability are analyzed. So that's it about the survivability with AIDS using ODE. So thank you so much for watching the video.